Hello, hello. All right, so we're going to talk about inference. Remember, inference is the process of using what's true for a sample to make a conclusion about a population. So inference, hypothesis test, confidence intervals for means, which means numerical data. So last unit was all about categorical data. So we were talking about proportions of things. So now we're going to move into numerical data. So we're going to calculate and interpret confidence intervals for a population mean, and then we're going to test a hypothesis about a population mean. In class, I went through and talked a little bit about this dude, William Gossett, why he's important, what he found out about when we're dealing with numerical data, and why we have to do things a tad differently when we're dealing with numerical data, specifically when we have really small samples, which is a lot of the time when we're doing numerical data. So we talked about what the t-distribution is and what's different about it compared to the normal model and how we have to kind of change things a little bit. I also went through about how we use or when we use a t-model and things about it, facts about it. And then we talked about how to use the t-table, which is another table that you are given on the AP exam to calculate certain values that you might need. I did note in class, and I'll note again, really it's only on potentially multiple choice questions where you might have to know how to use the table. Other than that, it's fine to use a calculator on a free response question to do a test or an interval. So we don't necessarily need the t-table to actually run a test or do an interval, but you may need to know how to use it for multiple choice questions. So I'm going to talk through some of our formulas for a hypothesis test and a confidence interval, just so you see what they are. Again, formulas on free response are not necessarily required as long as you name the test or interval that you're doing, but they will show up on multiple choice questions, so it's good to be familiar with the formula, at least somewhat. So, as we talked about, the big difference between using a Z or normal model and using a T in this type of situation, it all has to do with whether or not we know the population standard deviation or whether we know only the sample standard deviation, right? Now, generally speaking, we're always going to know the sample standard deviation. And what that does, the reason all of this matters is this just adding one more layer of uncertainty. All right, we're already using a sample mean to kind of come up with some kind of estimate about a population, but now we're also using a sample standard deviation. So there's just an extra layer of variability and uncertainty, and that causes things to look a little bit different, which is why we have to use a t distribution instead of a normal distribution. So just going through the formulas, remember that for a confidence interval, our basic generic formula is statistic, which for a means problem, that statistic would be x bar, the sample mean, plus minus, and then we have our margin of error, which consists of a critical value. So if we were just doing a regular z distribution, our normal model, we would use z star, and then times our standard error or standard deviation, which is the original standard deviation divided by square root of n. You may remember this back when we talked about sampling distributions with means. This was how we found the sampling distribution standard deviation. So that's where that came from. All right, so this would be how I do a interval, or how I calculate an interval if we happen to know the population standard deviation, which would allow us to use the actual normal model. So in a minute, we'll come back and talk about what happens if we don't know that. For a hypothesis test, the formula that we're talking about is the z-score formula, or the test statistic is what it's called. So our z-score formula is same as always. We take our observed value, which is what happened in the sample, or x bar. We subtract the mean, which would be mu. That would be our null hypothesis value, because that's what we're assuming to be true. And then we divide by the standard error, which is, again, the same formula, the original standard deviation of the population divided by square root of n. All right, so this would be how I find a z-score. Once I found a z-score, I would go to my z-table to find my probability, which is the p-value. But again, all of this would be if I knew the population standard deviation, which would allow me to use the normal model, which is very, very, very rarely the case in a means or numerical data problem. So what changes is, if I only know the sample standard deviation, there's all that extra uncertainty. So it makes me use a different model. I'm using what we call that t-distribution to find everything. So what changes in this formula, right? X bar is still X bar, but now my Z star changes to T star because we're using a t-distribution. And then, of course, instead of the population standard deviation, I'm using the sample standard deviation. So my actual formula looks a little like this. Pretty much the same formula. We're just making those small changes based on the information that I have. If you remember from class, we talked about how we find that T star using the T table. I also talked about how to find it using a calculator. And then the rest of this information would be given to us. For our Z-score formula for a hypothesis test, again, same general idea, but we're making some small swaps. It is now a t-score instead of a z-score because we're using a t-distribution. And then again, instead of population standard deviation, I would have sample standard deviation, which is S. So again, I would find that t-score, and then I could either use a t-table to get a p-value or a probability, but we could also use the calculator, which we will. So that is kind of the deal with formulas. So when I go through these examples, I will kind of show the formulas just so we're a little bit more familiar with how they work. But as always, it is completely okay to use the calculator as long as you name the type of test. So real quick, conditions. The first two conditions are going to feel very, very, very familiar because they are the same conditions we've used for the last unit and the unit before that. So do we have a random or representative sample? 10% condition checks for independence between trials. I will say for numerical data, this condition, it still applies. It's just really not as important, mainly because our sample sizes are generally pretty small. So it can be assumed. It's just not as important to check. So, and in general on AP exam, this condition is often not counted off, especially on numerical data or means problems. So from now on, I'm going to let you skip that one. Just know that it's never wrong to write it. So if you are not sure, you can write it. It's not a big deal. It's a good be in the habit of it, but it's just not as necessary anymore. So then our third condition is what checks for normality. With proportions problems, the way we checked that is that whole success failure or NP, NQ being greater than or equal to 10. For a means problem, it's not the same condition, mainly because there's no P. We don't have a proportion or a probability for a means problem because it's not that type of data. So we can't really check it the same way. So this goes back to, if you remember from sampling distributions, we had this thing called the central limit theorem. The central limit theorem basically said, in regards to shape, it said that even if our population distribution is not normal, the sampling distribution would be roughly normal as long as our sample size is big enough, which is typically around 30. So that's where this check for normality is coming from. So there are actually three things that I can check for here. The first thing that I can look for is, was it told to me that the population distribution is normal? So the population distribution is normal, then any sampling distribution that comes from that population will also be normal. So if that was given, then that's all I need to say. Given that the population is normal, move on, I'm done. That's rarely given. I'm just going to tell you that right now. We don't really know much about the population. That's the whole point of doing a confidence interval or a hypothesis test. So if we don't know that, the second way we can check this condition for normality is, do we have a big enough sample size? Again, that comes straight from the central limit theorem. Because if our sample size is big enough or bigger than about 30, then we know our sampling distribution, which is where all of this stuff is calculated, will be roughly normal, even if the population wasn't. Okay? So that's the second way. If our sample size is not bigger than 30. Our third way to check this is to draw some type of graph. We can do a graph as like a dot plot. We can do a graph on a calculator. I'll kind of show you both examples. Basically, we're checking to make sure that our sample distribution for this one sample that we're dealing with doesn't have any major skewness or outliers, right? As long as it doesn't have any major skew or outliers, then we kind of just assume that the population is roughly normal. It's sometimes a bit of a leap, but again, our goal is really not to check for perfect normality in the sample. We're checking for, can we at least take this and assume that the population's probably roughly normal? So you'll kind of see what we mean when we look at an example. That is our third way to check that condition, is to check a graph of our sample data. So before we get into our first example, we're going to remember what the steps are for a confidence interval and hypothesis test that we learned last unit. It is the same steps, even though we have a different type of data, we're still going to follow the same general steps. So for a confidence interval, we define the parameter. We check conditions, we calculate the interval, and then we interpret the interval. For a hypothesis test, write our hypothesis statements. Check conditions, calculate the z-score or t-score in this case, and p-value, and then write a conclusion. So those are our steps, same exact steps, just some of these pieces might change a tiny little bit, but we always follow the same exact steps. So let's look at our example. For the first one, we're going to talk about books. So a 2016 Pew Research study found that in a random sample of 1520 American adults, the average number of books read in the last year was 12 books with a standard deviation of 18 books. So that's our population data. We're going to construct and interpret that is not our population data. That's our sample data. Sorry. We're going to construct and interpret a 95% confidence interval for the mean number of books read by all American adults. So we have sample data. We're using that sample data to estimate what might be true about the population. So remember, first step, define the parameter. Now I know you're used to writing P equals or P1, P2 equals because up to now we've been dealing with proportions. The symbol we use for proportion parameter is P. But now we're dealing with means or averages. We're talking about numerical data, how many books someone read. And numerical data, we're going to find the average of it. So our parameter is now mu equals the true mean, whatever. So in this case, the parameter we are estimating with this interval is mu equals the mean number of books read in the last year for all American adults. So we have what's true for a sample. We're trying to estimate what's true for all American adults. Our second step is to check conditions. So our first condition is, do we have a random or representative sample? And we were in fact told that it is a random sample of adults. So I'm going to say given a random sample of American adults. Again, our second 10% condition still applies. It's okay to check it. You don't necessarily have to. I checked it on this one, so I'm going to just say assume 1520 is less than 10% of all American adults. Like I said, it's okay to skip this one. You won't get counted off for it, but it is there. And then our last condition checks for normality. Remember, there are 3 ways to check that. You don't have to check all 3. You're just checking one of the 3. So in this case, we were not told anything about the population shape. So we don't know that the population of the amount of books read by all American adults is normal. We weren't told that. But we do have a sample size of 1520, which is well over 30. So because our sample size is greater than 30, a normal model can be used. Basically, we know that our sampling distribution for averages from a bunch of different samples will be roughly normal. So it's okay to move forward. As we go into our next step, which is calculations, I just want to remind you that it is okay to skip the formula on a free response question about this type of problem, as long as you name the test you're doing. So what we're doing right now, we tend to call it a one sample t interval. T kind of indicates that it's going to be for means, because we use t for means. You could also say it's a one sample interval for a sample mean or something like that. But basically we have one sample and we're finding a confidence interval. So one sample t interval. So we're going to move into step 3, which is calculations. So I am going to show the formula just so we can kind of see how it works in action. But again, as long as you wrote one sample t interval, you wouldn't necessarily have to write a formula. So our formula says we're going to do x bar plus minus t star times s over square root of n, where s is the standard deviation, the square root of n is the sample size. So x bar is the sample mean. In this sample, the average number of books read in the last year was 12. So 12 plus minus T star we could get from our T table, right? We want a 95% confidence level. And then we would need to look up our degrees of freedom. Degrees of freedom is n-1 for a one sample test, which would be 1519. That won't be on your Z table. So remember, if they don't have the degrees of freedom you need, we always go up. Just kidding. We always go down. Sorry. We always go down to the next sample size because that's just making it might be a little bit wider than it needs to be, but it makes sure that our interval is as inclusive as possible. So we would go down to the next degrees of freedom and use that value, which would give me 1.962. Then I'm going to plug in S, which is standard deviation, so 18, divided by square root of n, which was 1520, and that is my formula. When I actually do the math on that, this is what I get, but let's talk about calculator. So in my calculator, the way I would do that interval, so I would go to stat and then tests, and what I'm looking for is T interval. So notice that my calculator does not actually say one sample T interval. There's a reason for that. It just says T interval. Notice that there's also an option for Z interval. We are not using Z interval or Z test up here because that would be if we just happen to magically know the population standard deviation. So those are still for means or numerical data, but that for those two, for Z interval and Z test, we have to know the population standard deviation, which we don't. So I'm going to use T. You will always use T for a means problem in this class. Then it asks for input, and it's data or stat. So data would mean that you actually have the average number of books read for each of those 1520. So if you had a list of actual data, we would use data. On this problem, I know the stats. I know the mean, and I know the standard deviation from that sample. So I'm going to go over to stats and push enter. I'm going to type in my X bar. The mean was 12. The standard deviation of the sample was 18. The sample size N was 1520. I want a 95% confidence interval, so 0.95, and then calculate. And lo and behold, it gives me that same interval that I calculated using the formula. So there is my interval. There your instructions will be on the slideshow for the calculator. And then we interpret that interval, right? We say we're 95% confident that the true, whatever we're trying to estimate, is between those two values. Make sure we include context, make sure we include all the specificity that we can handle. So we are 95% confident that the true average or mean number of books read in the last year by all Americans is between 11.09 and 12.91 books. Or we're 95% confident that for all Americans, they read an average of between 11.09 and 12.91 books in the last year. So that is our interval. And from there, we could do everything we did in the last unit. We could be asked to interpret the confidence level. What does it mean to be 95% confident in this context? So if I took many samples of 15-20 American adults, for each sample, calculated a confidence interval, about 95% of those intervals would include the true mean number of books read in the last year by all Americans. I could answer questions about, does this give me evidence? So if some expert about book reading said, I believe that the true average number of books read in the last year by all Americans is less than 10, then you could look and say, well, actually, my interval does not tell me that. My interval is completely above 10, so I do not have evidence that what you just said is true. So we could do all those same things that we did in the last unit, just for this type of data. All right, we're going to go into our example 3, which for some reason on my slideshow still says how many books, but this is actually about dissolved oxygen in a stream. So on this one, it says the level of dissolved oxygen, or DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A DO level below 5 milligrams per liter puts aquatic life at risk. A researcher measures the DO level at 15 randomly selected locations along a stream. And we have the results. All of these numbers are milligrams per liter for each of those 15 locations. Does this data provide convincing evidence at the alpha 0.05 significance level that aquatic life is at risk? Meaning, do we have evidence that the average is below 5 milligrams per liter? All right, so this is a hypothesis test. I know it's a hypothesis test because they asked me, does this data provide evidence? That's a good clue. We also are given a significance level, another great clue. We also were not asked to calculate an interval, which is another great clue. So this is a hypothesis test. We would call this a one sample t-test. And my first step is to write hypothesis statements. I'm going to start by defining the parameter though, because that'll help me write hypothesis statements a little bit quicker. So in this case, my parameter is mu. Again, we're talking about means. So mu equals the mean dissolved oxygen level for all water in the stream. So then my hypothesis statements, remember the null is always that things stay the same, right? Null is always just a statement of like, nothing changed, everything's the same, nothing's different, everything's where it was before. So in this case, my null would be that mu equals 5. So null is always something equals a number. Your alternate is what you think might be true or what you're trying to show is true or what you're trying to find evidence of. In this case, we're trying to find evidence that the average is below 5. So our alternate would be that mu is less than 5. Remember that your mu or your null and alternate should have the same number. Just the null is an equal sign. The alternate is less than or greater than or not equal. So that's our hypothesis. That's our first step. Second step is check conditions. So our first condition, do we have a random sample? We were told it was a random selection of locations on the stream. 10%, I'll skip that one this time. Again, it would be okay. It's kind of weird. We assume that 15 is less than 10% of all locations along the stream. Yeah, I guess. I'm just going to skip it because it's okay too for these types of data. And then for our last condition, we check for normality. So again, there are 3 ways to check that. Were we told that the population distribution was roughly normal? Nope, I don't see anything about that, so nope. Second is our sample size bigger than 30? Our sample size is 15, not bigger than 30, so we can't use the central limit theorem to get us through this one. So this is where we have to go with that last option. So one option is to use your calculator, and this might actually help you later. So calculator might be the way to go, but I'll also show you how we could just quickly graph a dot plot. I'll do calculator first though. So what I would do in my calculator is I would first go to stat and then edit, where I have my lists, and I would go ahead and type in all of the individual numbers in L1. So I'm going to pause my screen real quick and I'm going to do that, and then I'll come back. All right, so now that I have done that, I've got them in there. I'm going to go ahead and do second and then y equals. This will bring me to the stat plot menu. So I'm going to push enter on plot 1. I'm going to push enter to turn that on. I'm going to scroll down to type and move over to the right till I'm on top of the histogram option. And then I'm going to make sure that XList says L1. Once all that's set, I'm going to do second quit or second mode to get back to the home screen. And then I'm going to go, instead of going to the graph, I'm going to go zoom, and then I'm going to pick number 9, which says zoom stat. What that will do is zoom my window perfectly to where I can see the histogram that I've just created. So there is my histogram. And again, what I'm looking for on that histogram is major skewness or major outliers on one side of the graph, because that would indicate that possibly the population is skewed. This one is not something I would call majorly skewed. It also almost looks pretty roughly normal. It's not perfect, but it's definitely not majorly or obviously skewed. So what I would say for this is I would say something like sample graph of DO levels doesn't have major skewness, so we'll assume the population is roughly normal. You don't have to use that many words, but that is basically what we're saying, right? It's safe to use a normal model here because our sample data does not have any major obvious skewness. Right, told you I would show you real quick how to do a dot plot in case you forgot. So hold on a sec. I'm going to pause and then bring up something to do that with. All right, so I've got a little screen here. I just made a quick little line to represent a number line. I would look at my data. I see that my data goes from about 2.8. The highest one's in the 6s. So I'm just going to set up my number line to make sure that I have space for all of my data. So I'll do that real quick and come back. All right, so now I've got my little dot plot or my number line, and then remember a dot plot is basically just I would put a dot above the graph every time for a specific number. So for 4.53, right, there's 4.5, maybe a little bit above that. I'm just going to put a dot right above the number line. 5.04 would be maybe about right here. All right, we're not looking for this to be like perfect. We're just trying to get an idea of the general shape of the graph. So I'm going to finish putting dots for all of these, and then I will come back. All right, so here is my finished dot plot. It's not pretty, it's not perfect, but again, what I'm looking for is obvious or major skew, and I'm looking for just a hint that our population might be normal. So again, for this one, I don't see any major obvious skewness. It's a little bit more obvious because we can see individual dots, right? How spread out things are. But a major obvious skew on an example like this would be maybe a DO level of like 7 or 8 or 9 or 10 or something that's really far removed from the rest of the data. That might give me a clue that this population might be a little skewed to the right. But this data is pretty well contained and I don't see any major obvious skewness. So I think I'm going to say we're safe to go. So that's what that would look like. Always a good idea when you draw graphs to label your axis. So I might call this, DO levels if I could type or write quicker. But, we got this. So that is our conditions. Could take a little bit longer when you have to draw the graph or use your calculator to draw the graph, but there you go. So now that we've got our conditions, our third step is to do calculations. So again, I am going to show you the formula for this, but just know as long as you write one sample t-test, because we have one sample, and we're doing a hypothesis test with t because we're dealing with means. So one sample t-test, you do not have to show the formula. The formula that we're talking about, of course, is the z-score, or in this case, the t-score. So I'm going to write, there's my formula for t, right? X bar is the sample mean minus mu, which comes from the null hypothesis, divided by our standard error, s over square root of n. So X bar, sample mean, well, I don't know what that is. How could I figure that out? Well, I did just happen to, a couple of minutes ago, put my data in L1. So if you hadn't already done that for your graph, you would want to go ahead and do that now. So that's why I'm saying the graph or the calculator version of graphing your data is sometimes preferable because we're going to want that data in our L1 anyway. So I have my data in L1. So one thing that I could do is I could go to stat and then calc and then 1var stats. Right? There's 1var stats. I'm going to have it use L1 because that's where my data is, and then calculate. Right? And then X bar is our sample mean. So there you go. Sample mean is 4.77 minus mu. Remember my null hypothesis mean was 5. So I'm going to put 5 there. And then on the bottom we have S over square root of n. So S is our sample standard deviation. So SX, which is 0.94. Divided by the square root of n, our sample size, which is 15. Okay, so that's what our formula would be. I can figure that out and calculate it to be about negative 0.94 is our z-score, in this case t-score. Right? I could then take that t-score, go look at my t-table to estimate a p-value. We talked about that during class, how we use a t-table to estimate a p-value. But that's what I would do in this case. Instead, we're going to use the calculator. So the other way, you could use 1var stats to plug in the numbers for the formula. The other thing that you could do, though, is when you go to your stat test menu to actually run the test through the calculator, it actually gives you those values as part of it. So stat and then tests. And this one, we're going to do a t-test. So we're doing a hypothesis test. This means we always use t. You guys will never use z-test or z-interval like I mentioned before. We're always going to use t because we only know the sample standard deviation. And this one would be one where I'd want to use data. So I would want to go over and scroll and push enter on the word data because that means that I've put data in my L1 that I'm going to use for this test. So when you have it on data, we still need to type in our null hypothesis. So that's mu0 means our null hypothesis value, which was 5. And then you're telling it to use the list to find the mean and the standard deviation. from the sample and the sample size. And then we're going to go down and pick our hypothesis statement. We wanted to find evidence that the mean was less than 5. So I'm going to pick the less than option. And then just like in the last unit, we have the option of calculate or draw. I like draw because it draws me a little graph. Notice that my histogram is still back there, but I'm not going to worry about it. So there is my lovely t distribution. It's not actually a normal model, it's a t model, but it looks kind of the same. And then they've shaded off, so that place where it starts the shading, that is our sample mean, and then we wanted less than that. So we have our z-score or t-score of negative 0.94, and then it gives us our p-value of 0.1809. And that is our calculation step. So again, as a reminder, on your free response questions, right, you don't have to show actually the formula. If you write one sample t-test, that's fine, but you do need to tell me what t equals. You also need to tell me what the p-value equals. It's also a good idea to write what your degrees of freedom is. Remember, degrees of freedom is what's used to get the p-value. It basically determines what version of the t-distribution we're using. So in this case, degrees of freedom would be n minus 1. So 15 minus 1 is 14. I didn't put that on this slideshow, but I think that's a good thing to write as well. So then we would write our conclusion, and I forgot to actually type that out. So I'm just going to talk through it, and then I'll type it out in a little bit. So when you guys see the slideshow, it'll be there. But our last step is just like our last step for a proportions problem or proportions test. We compare our p-value to our level of significance and then determine whether we're going to reject or fail to reject the null, and then whether that means we have or don't have evidence of our alternate. So for this one, I would say since my p-value 0.18 is greater than my alpha of 0.05, right? That means that this whole sample mean that I got was not that unlikely to happen. Had an 18% chance of happening just by chance. So it's not that unlikely. So I'm not going to question that null hypothesis. So I'm failing to reject the null hypothesis, meaning I do not have evidence of our alternate hypothesis. We do not have evidence that the average dissolved oxygen level is below 5 milligrams per liter in the stream. We do not have evidence that the stream is at risk for aquatic life. So that is our conclusion. Again, I will write that out so that it's in the slideshow. And that's all I'm going to do for this video. I'll talk in the next video about the next couple of examples, which look through how we determine what sample size we need based on a margin of error. But that is it for now.